Okay, once you register for My Math Lab, you're going to want to come to this course name, 2016 Summer Math, 1342, DL Statistics. Click on this blue link. All your tabs are here on the left to do. The ones you'll need the most are the homework tab, where all the homework is, and next to each assignment is the due date. And you can also see the score, what you have on a particular homework. And the quizzes and tests. This is where you'll take your tests at the testing center. And they open up kind of like a homework, but with a test you have to have a password, so the testing center will have the password. So you won't be able to do these without taking them at a testing center. There's 4 tests and a final exam. You can look at gradebook to see all your individual grades. And chapter contents can pull up any section of the textbook. And then down here under course tools, there's a tab called, and I might have more tabs here than you'll see for yourself, but the one you'll be able to get to is document sharing. And this is where I have a whole bunch of resources available. There's another copy of the syllabus here. There's the orientation file that hopefully you've read through all of that. There's a stats, formulas, and tables. This is the formula sheet you'll get during every test. So if you print one out now while you're doing homework and practicing, you'll know what you have to memorize and what you won't. Anything on this you won't have to memorize. There'll be a lot of it on the first few tests that you probably won't use, but by the end of the semester you'll be using most of this formula sheet. The first test is only over chapters 1 through 3, so a lot of the formula sheet you won't be using yet, or maybe even know what's on there. Up here there's a lot of extra stuff too. I have some extra paper review sheets. One thing you should definitely look at is these notes and examples. I've done kind of a highlight of every section that you need to know with important notes and some examples of how they work. There's problem solved with technology. We're going to use this Texas Instruments type of calculator, TI-83, TI-84, the 2 best ones to get. And this can show you how to punch buttons in what you're doing in there. And all the examples I have in my notes, I have solutions for them too, so that way you can see if you're doing them right or not. So under the notes and examples, they're based by the chapter. So if you read through and do all the examples for chapter 1, 2, and 3 before you take your first test, that could definitely help. And then also do the review for chapter 1 through 3. And the solutions for the reviews are under the solutions as well. And then something new I'm doing this semester is these review videos, and if you go back to the main menu, under homework, besides all the chapter 1, 2s, and 3 sections, there's a total of 9 of those. You need to do all these by next Friday the 22nd by midnight. But the test is due the 21st on Thursday. So unfortunately some students ignore all this and try to take the test without doing any of this. They get a really bad grade on the test, and then they go, well, I got till Friday to finish these homeworks and I'll do them later. So they aren't due till Friday to give you a little extra time on them, but I would highly suggest at least trying every single one of these. If you don't get 100 on every single one before the test, that's fine, and then you have an extra day to finish them up and try to get as high a grade on each one. But if you're ignoring all or most of these prior to taking a test, that's not a good idea. Then if you scroll all the way to the bottom of the homework, I'm going to be adding these as the semester goes. I've created a new one, Practice Exam 1, chapters 1 through 3. So my review video is mostly going to be going over these practice exams. So if we click this one, there's 25 questions here. There's 25 on the test that are pretty similar to these 25. Click on one to try it. Most of chapter 1 is kind of learning the terminology of the branch of math called statistics, so a lot of it doesn't even involve math. Chapter 2, you get into charts and tables that are done in statistics. Chapter 3, you start doing some calculations. So you probably wouldn't even need a calculator for the first chapter, but after that you probably will need one. Here it says, how do a parameter and a statistics differ? And this is easy for me to remember, that parameter starts with a P and population starts with a P. So if you've read through my notes and read through the sections and tried some homework, you probably know this already. This should be a review where you're not learning this for the first time, but kind of reinforcing what you've already learned. Parameter is any kind of a measurement that involves a numerical measurement that goes with a population. So a parameter is a numerical measurement associated with a population. A statistic is a numerical measurement of a sample. This is choice A. And then, unlike the homework, this is like a test. So in the homework you can do all the things like show me an example or help me solve this or ask my professor. But in this, treat this like a test. Sit down, do all 25 of these like you're actually taking a test. It'll grade it for you. And if you don't get 100, then you'll know. You can go back and review the ones you missed, and you can see how much practice you still need to do. So I won't be able to, I don't think, yeah, I guess, okay, I was wrong about that. You can check these as you go. It is like a homework. Okay, so that one was correct. Number 2, determine whether the given value is a statistic or a parameter. So it says the mean salary for doctors is $45,000. So this is a little vague, but to be a statistic, it would have to come from some kind of sample. So if they gave me a number of doctors and it was a small number, or if they said they got it from asking people questions. Here it's a little vague, but it just says doctors, so I'm assuming that this means like all the doctors, if we could get every doctor and find out their average salary, that for an average doctor it's $45,000. So this to me sounds like a parameter because it seems like it's from a population. There's no mention of a sample here. So this is a parameter because it's a numerical measurement from a population, which is D. And that is correct. Okay, same question, but now a homeowner measures the voltage supplied to his home on 340 days of a given year. So here's the point of how you can tell this is from a sample. If it was a parameter like the last question, there would be no limit here of 340 days. A year is 365 days, so they're not doing every single day. They'd have to do every single day for it to be a population. Since it's some of the days and not all of them, that's what makes it a sample. So therefore it has to be a statistic, not a parameter. Statistics go with samples. S goes with S, P goes with P. That's easy to remember. So this would be D. It's a statistic because it's data collected from a sample, not from the whole population. Number 4, now we want to know, is it discrete or continuous? Discrete are things that you can physically count. Continuous are things that get measured. By their nature, discrete things are like individual points on a number line, like the number of students you have in a class. You can have 32 students in a class, you could have 33 students in a class. But you can't have 32.2. Nothing in between 32 and 33 is possible and discrete. Continuous is a whole range of measurements. Somebody could be 5'7" tall, somebody else could be 5'8" tall, but somebody else could be 5'7.5" in between the two. So I always answer these, it's based on whether you count or measure them, but sometimes it's hard to tell. So another way to tell is think of 2 examples that are close to each other, like 32 and 33. Could you get somewhere in between if you wanted to? And if the answer is no, then it's discrete. If the answer is yes, it's continuous. So when a bus is randomly selected, it is found to have a length of 16.84 feet. See, it could be 15 feet long, could be 16 feet long, could be 17 feet long, but it doesn't have to be 16 or 17 only. Here's an example exactly that it's 16.84, something in between the two, plus length is something that you measure. So this is an example of continuous, because the number of possible values is infinite and not countable. I cannot count them all because there's an infinite number of values between 16 and 17. If it was countable, then it would be discrete. When a car is selected at random, it is, okay, that's really the same question. Unfortunately, when you get these practice problems, it's generating questions from a bank, and sometimes it'll use similar questions even though I intended it for it to be slightly different. but we just saw that weight is continuous. It's continuous because there's an infinite number of values. That really was the same one. Now, one good thing about these practice exams is you can take them more than once. So the next time you do this, you'll see slightly different questions. So that way you could see something different there. In fact, if I go back and if I hit similar question, maybe it would give me something different. Yeah, see, here's a good one. When a car is randomly selected, it is found to have 2 wipers. Your car could have 2 wipers, it could have 1 wiper, but it can't have 1.6 wipers. You either have one or you don't. It's discrete because you count it. Discrete data because there's a finite number of possible values. Either it's 0, or it's 1, or it's 2, but it can't be anything in between 1 and 2. That's discrete. So sometimes you can even do, if you get a question wrong, you could do it again by hitting similar exercise, or if you get it right and you just want to see a slightly different version, hit similar exercise. Okay, nominal, ordinal, interval, and ratio. If you studied that in the reading of the textbook and in my notes, the way I remember this is nominal and ordinal are the first 2 levels, and as you move up levels, the characteristics start increasing of what you can do. So nominal is simply when all you can do is name things. Ordinal is names of things, but also has the added feature that you can put things in a meaningful order other than, say, alphabetical order or numerical order. Then interval and ratio are when you can also do mathematical ideas. Interval is basically where adding and subtracting makes sense. Ratio is when you step up and have multiplying and dividing also. Another way to think of interval and ratio is interval can have negative values where ratio has a true 0 and it's impossible to get negatives. So first thing I do when I see a problem is it something involving math or is it really just naming things? And sometimes just because there's numbers given doesn't mean that it's mathematical. Often it will be, but you can have numbers that are just used like names. Like jersey numbers on sports players aren't really, you don't take player number 7 plus player number 8, add them up and divide by 2 and get an average. But I can do mathematical things with this problem. Voltage measurements. Voltages are measured, so therefore you can do math with them. I could take 1.5 volts plus 3 volts, add them up and divide by 2 and come up with an average voltage which has a meaning. So clearly there's math involved in this problem. And that eliminates nominal and ordinal. Those are the non-mathematical ones. It's either interval or ratio. So one question is when you see like 3 volts and 6 volts, 3 times 2 makes 6. So there's a question is, could a 6 volt measurement of a battery be twice as much as a 3 volt one? And mathematically, yes, 3 times 2 is 6. But just because it's true mathematically doesn't mean for these problems that it would be something you could multiply. So again, the difference between interval and ratio is whether you can multiply and divide or not, but it also comes down to whether there's a true 0. If you cannot get negative values, that's what truly makes something twice as large as something else. So 6 is twice as large as 3, but only if you're comparing from 0, not if there's negatives that are possible. So can batteries have negative voltages? And the answer to that is no. If a battery's dead, it has no voltage, and there's no way to have negative voltage. So this is ratio because there's no negative voltages, and when there are no negatives, then something like 6 truly is twice as big as 3. This battery with 6 has twice the voltage as one with 3. Okay, rankings of musicians. So once I have a musician's name, there's not going to be any math to that. I can't take 2 musicians and take their names, add them up and divide by 2. That would be meaningless. Bob plus Sally divided by 2 is no mathematical meaning. So this is something that involves no math at all. It's just rankings, and that eliminates ratio and interval. So it's either nominal or ordinal. Names in general are nominal, but when you put a ranking on them, then Bob could be the number 1 musician and Sally might be number 2. But the difference between Bob and Sally could be very close or could be very far. And then if you go to the 3rd ranked one, that one could be a different difference. So because it's not an even amount of differences, then trying to do some kind of of interval or ratio doesn't make sense. It's not an even amount. So again, I've already eliminated math anyway from this problem. It's either nominal or ordinal, and I would say ordinal because rankings make order important. It's better to be the number 1 ranked musician than number 2. You'll get more prestige, more money, more fame. So that's what makes it ordinal. Okay, identify the level of measurement. So now they give me an example and I have to say, is it nominal, ordinal, interval, or ratio? In a survey of responses of respondents are identified 0 for a yes, 1 for a no, 2 for a maybe, 3 for anything else. The average is calculated to be 1.1. So we do have some math here since there's an average going on. And just also with these levels is nominal is the lowest level, you just name things. But when you move to the next one, ordinal, now you have all the categories from before plus the new feature that things can be placed in order. Then when you move to interval, you still have all these ideas from before that there's names and there's an order to them, but now interval adds the fact that you can do differences. So the difference between a 0 and a 1 could have some meaning, and then the difference from 1 to 2 could have a meaning. But the differences may not be meaningful is the problem. Going from 0 to 1 could be different than going from 1 to 2, which could be different from going from 2 to 3. And plus we're kind of just putting numbers on these things. Even though a mean was calculated, I'm suspecting that this problem, that this average is kind of meaningless. 1.1, why would that be like a yes or a no? That's kind of meaningless. Because these values are just arbitrarily assigned to the names. This is really not really mathematical in my mind. And there is kind of an order here, but it's really a meaningless order because I could switch the order and still do the same problem. So I'm thinking that this one is nominal because even though there's somewhat of an order that seems to be here, there's somewhat of a math that seems to be here, they're really meaningless things. The order here is meaningless, the math is meaningless, this is nominal. And that's what some of these problems can be hard like that, where it seems like there's some math involved or seems like there's an order involved. What is wrong with the given calculation? It may be that the average was calculated wrong, but that's not really the point here. Such data are not counts of or measures of anything. So the average needs to be computed. No, that's not it. Such data are not counts or measure of anything, so it makes no sense to compute their average. So the 0 is just being assigned to the word yes, but I could easily assign the number 2 to that. There's no purpose for 0 being assigned to the yes. And why does it have to start with 0? Why can't it be a 1 for yes, a 2 for no, a 3 for maybe? So this one's C because it's meaning all the assigning numbers to these and doing a calculation is kind of meaningless here. So that's where you got to be a little careful on some of these. Which one is not a level of measurement? And here's how I remember it. It goes nominal, ordinal, interval, ratio. One time in a class I had the class come up with an acronym to help remember this better, and we voted on the best one. And it actually happened in the year 2005 when that hurricane hit New Orleans. Somebody came up with New Orleans is ruined, because at the time it was. And that's exactly the order. If you remember, New Orleans is ruined, that's N-O-I-R. So that way you can remember nominal, the N1 is first. New Orleans, O is second. Is I, so interval's third. And R, ratio, is fourth. They don't have interval here. And quantitative is not one of those four. Which of the following would be classified as categorical data? So we say discrete are things that you count, continuous are things that you measure, and then categorical is everything else. So which of the following is categorical? 3 of these 4 should be things that you count or measure, and then there should be one that you don't. Amount of rainfall can be measured. You could get 10 inches of rain, you could get 11 inches of rain, or it could be 10 and a half, anything in between. That would be continuous, that's a measurement. We've already seen height and length are measured. A tree height could be 50 feet tall, could be 51 feet tall, or it could be 50.6 feet tall. That's another continuous one. It's a measurement. Anything in between is possible. Number of suitcases on a plane. There could be 100, there could be 101, but there can't be 100.8 suitcases. That's a discrete thing. It's something you count, and you can get 2 examples, but you can't get in between them. Hair color is neither counted nor measured. You can't count it, you can't measure it. So that's what categorical is. Categorical is anything you can't count or measure. Determine whether the description corresponds to an observational study or an experiment. Now, observational studies and experiments are similar in the way they are processed or done. The main difference is, in an experiment, we try to create groups that get randomly assigned treatments, and we hope to show a cause and effect if all the possible variables of the experiment are the same, and then the one thing that's different is the treatment that we randomly assign. In an observational study, you don't really assign these treatments randomly. The treatments may be picked by the individuals, they may be doing this already, the results may already be done and you're just looking up results. All those things are an observational study where you're not imposing the treatment on somebody randomly or something. And in the case of it, people will use these just to get an idea what's going on, but the disadvantage of observational studies, you wouldn't be able to show cause and effect no matter how strong the results might come out to be. So research is conducted to determine if there's a relation between brain cancer and the use of cell phones. So some of these are hard to answer because they're not giving me enough information to tell, is this going to be randomly selected or not? Another thing to look at when you're given these kind of problems is, would it be ethical to do this as an experiment? To truly do this as an experiment, I would have to get a bunch of people together, put them in two different groups, and then randomly assign one group would get cell phones that could possibly cause brain cancer, and another group would have to get some kind of possible alternative treatment, or possibly what they call placebo, a fake treatment. So they're using cell phones somehow that don't actually work to where they wouldn't give somebody brain cancer. But the process of going through and pretending that you're making calls, the person wouldn't know that the phone actually didn't work somehow. So this seems kind of hard to do as a true experiment. Not only would it be hard to get a fake cell phone that somebody actually thinks is real, but it would be unethical to do this on somebody and see if they get brain cancer or not. So doing a true experiment is definitely out of the question on this problem. So when I read these, I try to say, could I do an experiment if it was possible? And here, it's not only hard to do, it would be very unethical to do this. So here's a case where an observational study is useful, because they're not as good as experiments, but this is something where people are already using cell phones. So let's just use the information we already have. We probably have cancer rates from doctors from the past on how often people got brain cancer in the past. And now we have people have been using cell phones for a couple decades. So if maybe there's a great increase in brain cancers all of a sudden now in the modern times, that could be cause for alarm that maybe cell phones are causing them. Although seeing that from an observational study doesn't prove a cause and effect there. If you see some alarming thing like that, then maybe you'd want to up this up from an observational study to an experiment if there was an ethical way to do it, if you want to actually show cause and effect. But this clearly sounds like an observational study because you would be looking at stuff that's already gone on. You would use records from the past, even records from right now, but based on what people have been doing for a while. This is not an experiment where we randomly assign these treatments to people. Okay, determine whether the given description corresponds to an observational study or experiment. In a study of 370 boys with a particular disease, the subjects were photographed daily. Okay, so again, it kind of sounds like they're more imposing things here, but just taking a photograph of somebody is not really imposing a treatment on them, especially not randomly. So this again sounds like an observational study because all they're going to do is photograph them and look at stuff. So the description corresponds to an experiment, corresponds to an observational study. There's not enough information given. And that a lot of these problems actually sound like C could be the answer to them. In a study of 370 boys with a particular disease, the subjects were photographed daily. Let's see if it's observational study. It's definitely not an experiment. Yeah, okay. I was somewhat leaning towards C, that maybe it was not enough information, but fortunately most of these questions like this sound like there's not enough information. Okay, then we have the 5 main ways to take a sample. Ideally, we'd like random sampling, because doing things randomly eliminates human biases and all these things that you can't plan for. Unfortunately, random sampling is often the hardest way to take a sample. So we have some lesser ones that are sometimes okay, sometimes not, depending on how they're done. One sampling that's the worst, though, is convenience sampling. It's real easy to do, but it's highly biased. You hardly ever get any useful information from it. This should be avoided at all costs, even though it's actually done all the time. The other 3 have some uses. Systematic is when you do every so often somebody. So get a list of people and take every 10th person on the list. Or go stand somewhere in a mall, every 20th person that goes by. It's not as good as random, but at least it mixes it up a little better than convenience, where you're just picking whoever you want. Cluster is when you take whole groups at a time. So maybe you go to a mall and you pick everybody from a certain store. Or take a sports league and pick every player from one team. That would be a cluster sampling. Stratified is when you take some from every group. So at a mall, I could take a few people from every store, or a sports team, a few players from each team. A man is selected by a marketing company to participate in a group. The company says the man was selected because everyone in 5 randomly towns was being selected. Everyone in whole towns at a time. So this is a cluster sampling where I'm taking whole groups at a time. Okay, a radio station asks its listeners to call in their opinion. See, this is what the easiest kind to do, and it's done all the time, but it's the worst type of sampling, convenience, because it's highly biased. It leads to answers that are only come from people with strong opinions. So it's easy to do, and people do it all the time because of that, but it's a very meaningless way to sample. You get a highly biased sample that's often nothing like the real population. Okay, determine customers' opinion for food quality. They select 120 city blocks and survey all homes within that block. So again, you're doing all at a time. That's always cluster sampling. And again, I don't know if I go back to this question and hit similar exercise, will give me something that's not cluster sampling. No, that one's cluster again. Okay, but you can play with that a little and see if you can get a different answer to come up, or you can go back to the homework over that section, and they have one of every type in the homework too. Blank are sample values that lie very far from the majority of sample values, and this is a term called an outlier. An outlier is far from the rest of the data. A blank distribution has a bell shape. This is something we study a little bit in chapter 2, and then we have a whole chapter on it later called the normal distribution. So in chapter 2 it gets introduced just so you'll be able to deal with it better later. Okay, a bar chart and a Pareto chart both use bars to show frequencies of categories for categorical data. What characteristic distinguishes a Pareto chart from a bar chart, and how does that characteristic help us in understanding the data? The most distinguishing feature of a Pareto chart is the bars descend in order from highest down to lowest, left to right. So a Pareto chart has bars arranged on a non-zero axis? No. Pareto chart, the bars are arranged in descending order? Yes. Depicted as slices of circle? No. Cumulative? No. So it's B, and then the second half of this is going to be why it's important. The Pareto chart helps us understand data by drawing attention to the more important categories, which have the highest. So you'll see the highest one right away first, and it'll draw your attention to it. So if they're trying to solve some problem, you'll know what the biggest issue is right away. Okay, the data represent the heights of eruptions by a geyser, and use the heights to construct a stem plot. Is there strong evidence that the data are not from a population have a normal distribution? So one thing I do is I look at the choices. There's a 9-0 for 90, then there's another 90 here, but then there's a 9-0, 9-5, 9-6. So each time there's another number in the stem, that's a different data value. So the 0, 5, 6 in the first row would mean that there's a 90, a 95, and a 96. So I could check here how many 90s are there in the whole data set. There's only one 90. So it can't be C because that should have had a 95 and a 96. I can check A and B. What's different about them? A has 14 with a 0 and B has 14 with a 0 and a 7. So there's definitely 140 in the data, but is there also 147 or not? Yes, there's 147 here. So it has to be B by process of elimination. Then you want to look at this, and here's an advantage of a stem plot. If you trace along the stem values with your cursor or finger, would this shape be at least approximately bell-shaped or normally shaped? It doesn't have to be perfectly symmetrical or perfectly bell-shaped, but as long as it's close to it, then you could say it's approximately normal. You would need something like C. This is what's called uniform when they're all the same. Or even A, it's kind of got a high point, comes down low, then it goes back up high again, then goes back down low. So that's definitely not normal, and C is definitely not normal, but B, it's not perfectly normal, but it's at least close enough where the data values are low first, then they kind of reach one high point, and then they go back down low again. And the high point's near the middle at least. So yes, the distribution is not dramatically far from a normal distribution. So there is strong evidence against the normal curve. That's not right. The distribution is dramatically far now. No, the distribution is not dramatically far from a normal distribution. So there is not strong evidence against it. See, the one issue with this is they're saying it in a negative way. And that's kind of what you do with these is you can assume a normal distribution as long as it's not dramatically far from it. So this one's A. And the question says, is there evidence that it's not far from it? So no, the distribution is not dramatically far from it. So there is not strong evidence against using one, because we want to use one when we can. You got to be careful when you read these things how they're stated in a negative fashion. Okay, now we hit chapter 3 where we can start using the calculator. So there's 1, 2, 3, 4, 5, 6, 7 numbers given, and they first want the mean. Here's where using a graphing calculator can be helpful. If you press the Stat button, and then you get to a screen called Edit, if you press Enter, you go into what are like spreadsheets. These are called lists of data where you can type data in. And if you have data already typed into a list, this is list 1 here first, I can up arrow and get to the top of the list where it says L1, and while L1's highlighted, if I hit clear enter, it wipes out the whole list, so I can type a new problem in. So now I'm just going to type these 7 numbers into list 1, and the order doesn't matter. 368, enter. 529, enter. 350, enter. 324, enter. 372, enter. 513, enter. 567, enter. Just be careful on a test to double check and look at each number you typed again, make sure you don't have any typos. You can get the mean quickly by hitting second quit, second stat, go over to math, and choose the one that says mean. When you press enter, it'll select the mean, and now there's a parenthesis and it wants to know the mean of what, because it doesn't know what you want it to find the mean of. I want it to find the mean of the numbers in list 1. You can tell it list 1 by hitting second and the number 1. And then if you press enter, it'll tell you the average or the mean. 431.857. Be real careful when you're answering questions mathematically in my math lab. Often students will get an answer essentially right, but they're not putting it in the way the program needs it. And on a test, you only get one chance to get these right. So it says round to 1 decimal place. Always read the blue part before you think you're done and make sure you actually have what they're asking for. Round to 1 decimal place. 431.85. To round to 1 decimal place, you want to look at the second decimal place. The second decimal place is a 5. If it's 5 or higher, you round the first one up by 1. So I'm going to add 1 to the 8 and make it a 9. 431.9. Okay, the median can also be found in the calculator if you hit second stat, go over to math, right below the mean, the fourth choice says median. So you can do median of list 1 and it says it's 372. These can also be done the old-fashioned way if you want to. You can add up all 7 numbers, divide by 7 to get the mean. You can put the numbers in order, try to find the one that's in the middle. It'll be 372. But the calculator can help to make sure you get it right and to do it quicker, basically. Okay, mid-range is nothing the calculator can do, but the mid-range is found by doing the smallest number plus the biggest number and dividing by 2. So one thing, especially if you get a longer list of numbers, is you can put the numbers in order so you can find the smallest and largest numbers quicker. Press just the stat button alone without hitting second first. Stat. Where we put edit is where we put all the numbers in, but right below that there's one called sort A. This will sort your data in ascending order from lowest to highest. So sort A, choose that one by pressing enter. Tell it L1 so it knows which one to do. It says done. In that instant of a second, it just put all the data in order. So I typed the data in all mixed up and now they're in order. So if you go back to where the spreadsheet is, press stat, press enter for edit. Now I can see list 1 and now I can see all the numbers in order. The smallest number is the first one now, 324, but I actually typed a 368 first. So it sorted the data for me and put 324 first. And then I can go to the bottom of the list. The biggest number is the last one, 567. So now I know 567 and 324 are the smallest and largest. 324 plus 567, enter, divide by 2. The mid-range is kind of the average of the largest and smallest numbers. So that's 445.5. Round to 1 decimal place is needed. Always check that before you submit the answer. Yes, there was no rounding to do because it came out exactly to 1 decimal place. Okay, the mode also cannot be done in the calculator. You can't just spit the mode out, but after you've sorted the data, you could just go through them one by one and check, do any numbers repeat? 324, 350, 368, 372, 513, 529, 567. If there's any repeats after they're sorted, they'll be in order. So since there's no repeats, then there's no mode. To have a mode, there has to be at least one number that's more often than the rest. If every number occurs equally, there's no mode. If every number occurs once, no mode. If every number occurred twice, it would be no mode. If every number occurred 10 times, no mode. But if there's at least one number that occurs more than others, then you can have a mode. There can be a lot of modes. If there's 2 1s and 2 2s and then other numbers occur only once, then the mode could be both 1 and 2. If there's 2 1s, 2 2s, and 3 3s, then the mode would only be 3. So it's not necessarily all the repeats. But if you had 2 1s, 2 2s, 2 3s, 2 4s, and a single 5, then the mode would be 1, 2, 3, and 4. All those ones tied for the highest. Which car appears to be the safest? So again, you're looking at the mean here. Listed below are head injury measurements from small cars that were tested in crashes. The measurements are in HIC, which is a measurement of a standard head injury criterion. Lower HIC values correspond to safer cars. So listed below correspond to the cars A, B, C, D, G respectively. Okay, so which car appears to be the safest? I guess you could just tell that from the actual numbers themselves. The lowest one is 324. That's the fourth one. A, B, C, or D, that would be D. Car D appears to be the safest. Based on these limited results, do small cars appear to have about the same risk of head injuries in a crash? And I would say no, because there's a big range of values here. 324 compared to 567, that's almost double. So no, because the data values do not differ substantially. No, because the data values differ substantially. That's the problem, is there's a wide range of answers here. Okay, the range is another thing that you can measure that measures spread of data. The range is simply the biggest number minus the smallest. So maybe you could find it by searching for it. If you can't, or if the data is really long, maybe you'd want to type it in your calculator and sort the data. Then you could be sure you have the smallest and largest. For me, it might be easier here to search for it. And actually, it looks like the orders are in reverse order here from largest to smallest. So the smallest is 13.7, the largest is 42. The range is the biggest number minus the smallest. And that's 28.3. Type an integer or a decimal. So we would say 28.3 million. Okay, variance could be done with the calculator. If I put all the data in list 1, so I go stat and edit, go up to the top and hit clear enter. Now you can type the new problem in: 42, 40, 39, 33, 22, 21, 19, 15, 14.9, and 13.7. The data do not have to be in order to do things like the mean or the median or the variance or the standard deviation in the calculator. By hitting second quit to get out of the screen, second stat, and go over to math, you can do the mean, the median, the standard deviation, the variance. So I would just go down to variance, list 1, 128.3871111, round to 2 decimal places. You see, you got to be real careful. From answer to answer, they'll switch this sometimes and go from 1 decimal, then the next question might want 2 decimals, and if you don't read that, you can totally get an answer wrong just by not reading that. 128.387. So I want 2 decimal places. I look at the third decimal place. It's a 7. So that's enough to round the second digit up by 1. It was a 38. Now it's going to be added 1 to become 39. The standard deviation is always the square root of the variance. So I can either square root my answer by hitting second square root. And if you hit second and the negative key, it'll grab the whole previous answer. Or if you forget that fact that the standard deviation is always the square root of the variance, you can also hit second stat, go to math, and just have it do the standard deviation for you. The standard deviation of list 1, in total, it totally agrees with the square root of the variance, 11.3308, on and on. Round to 2 decimal places, 11.330, so the 0 in the third slot is not big enough to round the 33 up. It's going to be 11.33. Is the standard deviation of the sample a good estimate of the variation of salaries of TV personalities in general? And there's some things to look for here. One thing you could read, it says no because there's an outlier, so that's an issue. If there's an outlier, that could cause it not to be a good estimate. So the highest number is 42, but there's a 40 pretty close to that. The lowest number is 13.7. 14 is pretty close to that. So an outlier is one that's really, really far from the rest of the data. If there had been a 40 was the second biggest number, if the last number was like 82 instead of 42, that would be an outlier. And later we'll have a way to define whether it is definitively or not, but at this point we can just eyeball and say, yeah, none of these numbers are significantly far from any other one individually. So that's not an issue here. No, because the sample is not representative of the whole population. That's another issue. If I want to know what's the average height of a person at a school, I wouldn't want to go down and ask the basketball team and get all their heights, because basketball players tend to be taller than other people. So finding the average basketball player's height will not represent the average person's height. So where did they get this data from? Where did they get this sample from? Listed below are the top 10 annual salaries of TV personalities. But it's the top 10. The top 10 TV personalities are going to be paid the most. So they're not representative of all TV personalities in general. So this is no, because using the top 10 people only is nothing like the average person. So that's what you got to worry about when you're looking at samples. Where did they come from? That's a biased way of sampling, actually. Heights of men on a baseball team have a bell-shaped distribution with a mean of 169 and a standard deviation of 9. Using the empirical rule, what's the approximate percentage of the men between of the men between the following values. Okay, so what you do is I take the mean 169 and I make a little number line and put that in the middle of the number line. Put 169 in the middle of a number line. Then take the standard deviation of 9. The empirical rule goes out to 3 standard deviations. So if you take the standard deviation of a 9 and add that to the mean 3 different times. So I would be doing 169 plus 9. That's 178. So put that second on your number line. 169 would be in the middle. 178 would go next. Then add 9 a second time. 187, put that next. Add 9 a third time. 196, put that next. So you'd have these numbers on a number line. Then go back to the 169 mean and subtract 9 3 times. 169 minus 9 is 160. Minus 9 is 151. And minus 9 is 142. So you'll have 7 numbers on a number line. The 3 below the mean will be 4th, and then the 3 above the mean. If you do that first for any of these empirical rule problems, you'll have any number they could possibly ask you for. So in part A it says 142 and 196. Put your finger on the mean and count how many places below the mean and how many above the mean each of these two numbers are. They're going to be 1, 2, or 3 each. And they should both be the same also. So the 142 was the third one I did below the mean. So that's 3 below the mean. The 169 was the one that was 3 above the mean. They should both either be 1, 2, or 3. They're both 3 away. Then you memorize in the empirical rule the 3 percentages. 68 is the percentage for 1 standard deviation. 95 goes with 2, and 99.7 goes with 3. In fact, the empirical rule is sometimes called the 68, 95, 99.7 rule. Because these two numbers are both 3 places from the mean, then I pick the percentage that goes with 3, 99.7. 151 and 187. 151 was the one that was 2 away, so 187 should be 2 away too, and if I drew the number line out, I could physically count with my finger. Those are both 2 places away from the mean, 2 standard deviations from the mean. The percentage that we memorize that goes with 2 is 95. So these answers will always either be 68, 95, or 99.7. And you just count how far away from the mean you are, you can figure it out. Okay, height of 63. Okay. Was the shortest president of a particular club in the past century. The club presidents in the past century have a mean of 66.7 and a standard deviation of 1.7. What is the positive difference between Vincent's height and the mean? So if you take his height, 63, and do a minus for a difference, the average is 66.7. 63 minus 66.7 is negative 3.7. So his difference is he's 3.7 inches below the average, but the positive distance would be 3.7. So they just want to know how far he is from the mean, ignoring if he's above or below the mean. The positive distance is 3.7. How many standard deviations is that? Well, a standard deviation is 1.7. So if we divide this 3.7 by 1.7, 2.17, type an integer or a decimal rounded to 2 decimal places, 2.176, so 2.18 standard deviations. So taking how far away he is and divide by the standard deviation will tell you how many standard deviations away he is. He's 2.18 standard deviations from the mean. A z-score is in essence this calculation, although it takes into account positive or negative. Since he's below the mean, he's actually negative 2.18 standard deviations from the mean. A z-score is the number of standard deviations from the mean you are, but positive if you're above the mean, negative if you're below the mean. And a z-score is unusual if it's 2 and above or negative 2 and below. This is unusual because negative 2.18 is lower down than negative 2. If you put it on a number line, if you're bigger than 2 or less than negative 2, then you're unusual. If you're between 2 and negative 2, like a negative 1 or a positive 0.8, those would be usual. This one's unusual. And that's a prelude to a future chapter where we'll do that more. Okay, well, one of the tallest living men has a height of 241 centimeters. One of the tallest living women is 236. Men have a height with a mean of this, a standard deviation. Women have a mean and a standard deviation. Here's where z-scores are actually useful. Relative to their population, who is taller? So the taller person is the one with the larger z-score in general. So I can calculate a z-score for each one of these people. Take the person's actual height. The tallest man was 241 centimeters. The average height for men is 173. So you do the person's height minus the average, press enter, and divide by the standard deviation. It's very similar to that last problem where we subtracted and divided. Divide by 6. The man has a z-score of 11.33333. So that's a highly unusual one because it's way past 2. But if the woman's z-score is bigger than 11.3, then she'll be relatively taller. If hers is less than 11.3, then she'll be relatively shorter. So do the same thing for the woman. Take her height, 236, minus the height of women. Average height of women is 167. Divide by the standard deviation for women, 8. Hers is only 8.6. It's still highly unusual compared to other women, but it's not relatively taller than the man. So the man is relatively taller because the z-score for his height is greater than the z-score for her height. It's D. That's where z-scores are useful. Another common use for them is if you take tests on different scales. Take a SAT test and an ACT test, and you want to send the better one to a college to get into a college. Well, it's not a fair comparison because SAT scores are in the hundreds and the thousands, where ATC scores are single and double digit numbers. So getting a 1600 on an SAT may or may not be better than a 27 on an ACT because it's just physically bigger doesn't make it a fair comparison. But if you did a z-score of each one, then you could see which one's relatively better. Okay, lastly, the following are the duration time in minutes of missions flown by a space shuttle. Use this to construct a box plot and a 5-number summary. The calculator can handle this too. If we go to Stat and Edit and clear out the data that's in there, put all these numbers in any order. I just put them in as they come. 8, 7201, 8659, 8784, 9936, 10,082, 10,149, 11,410, 11,538, and 11,833. So notice all the numbers are between 7,000 and 11,000 except for the one that's an 8. That was one of those space shuttles that unfortunately blew up during the takeoff. It only lasted 8 minutes. That would be an outlier. That one's far from the rest of the data. All the data is between 7,000 and 11,000 except for one that only took a few minutes, unfortunately. So there's a clear outlier. A 5-number summary is a way to show a box plot. And what it's composed of is the minimum value, which we already know is 8. Then you put the lower quartile second, the median third, the upper quartile fourth, and the maximum numbers last. So since these data appear to be in order, I can already tell that the maximum is 11,833. But if the data was mixed up, we can get that answer too. The calculator will actually spit out the 5-number summary. If you press Stat and go to Calculate and choose the 1var stats, the very first choice, and then press enter to do it. And you get all this data here that you probably don't even need to know yet, but there's a down arrow, and if you down arrow 5 times, 1, 2, 3, 4, 5, it takes me to the bottom of this list, and there's the 5-number summary. It's got minimum first, 8, Q1, that's the lower quartile, it's the 25% mark. It's kind of the median of the lower half of the data. 8659, so that would be the second answer. 8659. The median is 10,009. 10,009. There's actually 10 numbers here, so the median isn't even one of these. the median is the average of two numbers in the middle. So 1, 2, 3, 4. There's the 4 lowest. 1, 2, 3, 4, 4 highest. The two in the middle get averaged together to make this median of 10,009. The Q3 is the upper quartile, 11,410, which actually is a number in the data set, because if you separate the 5 lowest from the 5 highest, if I cover up the 5 highest numbers, what's the median of the 5 lowest numbers? Well, there's 5 of them, so there's one in the middle, the third one. 8659 is the median of the lower half. That's what the lower quartile is about. If you cover up the 5 lowest numbers, the 5 highest has one exactly in the middle. That's 11,410. That's the upper quartile. So you can do it by hand or by calculator. Now we need to get all the way down to 8, so that's why this one's going all the way down to 8. This one is, there, it looks like it's almost at 0 virtually. So the answer is definitely not C, because this isn't going down to 8. Another way to tell is look for these things. 8659, that's the front of the box. So could this be 8659? 8659, it looks like D's out because that's too far down. That's close to 7,000. The median's 10,000. And the upper quartile is 11,000. The difference between 10 and 11,000 is a little over 1,000. It's also about the same distance from the median to the lower quartile. So it looks like the median, which is the center of the box, it's about equal away from both sides. So that's why B appears to be wrong, as the median line is too close to the lower quartile and too far from the upper. It's about 1,100 this way and 1,100 that way. So to me it looks like it's A. Yep. And then if I save this, now you can see all the ones checked green are right, and because I was doing this as a homework, they were able to tell me each time I did one if it was right or wrong. So if you get 100 on it and feel good about it, then you'll be pretty prepared for the test. If you missed questions and had to do them repeatedly to get them right, then that tells you you need to practice more. And then the best thing to do before you take a test is make sure you've tried all 9 of these homeworks, the 3 from Chapter 1, the 3 from Chapter 2, and the 3 from Chapter 3, and have decent grades on them all. And you can do them all as many times as you want. Even if you have 100 on assignment, you can hit similar exercise and do it again. And then if you get it wrong the second time, you can say, save my best result, and you won't lose your good grade. So there's definitely no reason to wait on these. Do them all until you have good grades on them. Then scroll to the bottom, do this review for the practice exam. That's going to count as a homework grade also. And then go to my document sharing and make sure you read all the notes and examples, look at the solutions. The review sheet can help. That's some more practice that has a few more cases maybe. So there's plenty of stuff here to get you prepared. It's all a matter of do you have the time to do it or not. Too many students wait and to the last minute to do all this, and there's not enough time to do it all. You got to do a little bit every day. As I mentioned in an email, I would take 2 days per chapter, and that would give you 2 days to review and study. As of right now, the class started yesterday. We're already in the middle of the second day. Students should be finishing up Chapter 1 today, and yet if I go to the course page, out of 32 students in the class, only 20 have signed up for the course already at this point. So we already have 12 people that haven't even started yet, unfortunately. And of these 20, some are just signed up and haven't done anything yet. So as always, email me if you have any questions, and try all this stuff in here. There's people that get really high grades on tests that take the time to do all this stuff. And there's people that get horrible 10s and 20s on tests because they just take the test off the cuff without practicing anything. And they can sometimes get really low grades too because they don't practice putting answers in. You got to read carefully. What do they want? Where do you round decimals to? So watch out for all that. But if you have any questions, let me know, and I'll be doing these reviews for every test.